So my name is Bryan de Goeij and I'm working as a senior system engineer for TNO. And exactly system engineering for optical space instruments. And that means that I'm in the end responsible for delivering optical instruments that are measuring Earth, but also deep space to the space agencies around the world. And meaning technically responsible means that I have to ensure that the optics are okay, but also that in the end the system can be launched. It can survive up to all the space environments, so it should survive radiation, the vacuum, etc. I think engineers ensure that the wishes of scientists can be incorporated in the end. Engineers are capable of making systems that are adequate and sufficiently good for measuring the effects that the scientists would like to see. So scientists tend to focus on a lot of the details, while engineers are usually more balancing real-life capabilities with the needs that are necessary for doing the science. The working day for a system engineer is very diverse. So when I get in the morning, I usually have an idea of I want to tackle these problems in mind. And that's what I start working on. And also having a number of people I want to visit during the day to see how different disciplines are going. But usually after 2 or 3 hours of work, some of the people walk into my office and they share their newfound issues and problems with me, and I get distracted and taken away about solving those issues first. Because typically when the specialists come to me, they are high priority issues or high priority problems that need to be solved as quickly as possible actually. What I enjoy most about my work is that I'm working as a system engineer really into the heart and the core of a team. I have to ensure that all the team members can do their specialized jobs, and I also make sure that the work of everybody is in the end technically aligned with what the customer needs. So I'm actually the interactive person between all the different disciplines, interaction with the customer, ensuring that if we cannot meet a certain request from the customer, I have a discussion with the customer what we still can do, or how we can solve it, or how we can still ensure that the customer can do what he in the end wants to do with the system. The worst thing about my job is a lot of the documentation that needs to be written. Because in the end, if you work in the space environment, if you build a system that is, let's say, 8 kilograms, then you have to deliver with the system a 80 kilogram pile of paper. So typically the amount of paper weight is much higher than the system that you deliver. But in the end, it's necessary because when you send something off into space, it will work or it will not work. You don't get any chance of repairing the system. Actually, there are 2 proudest moments in my career. When I just started working at TNO, I was responsible for a bit smaller systems. So at that time I was developing a sun sensor system. So that's a system that can measure based on where the sun is, the orientation of the spacecraft. And the first time when you deliver space hardware to a customer, that it gets mounted onto the spacecraft and that you get the first signals back from space and that you see that everything is working perfectly there. That was the first proudest moment in my career. That was a few years ago. And during that time we were sitting with the entire team actually in this same area over here, watching a live feed from the launch and waiting for a confirmation from the customer that the system was working well. So that was the first proud moment, and the second proud moment is actually the system that's standing here besides me. And that's the work that I've been doing for a scientific space instrument called the multispectral imager, which is an instrument that will be part of the ESA EarthCare mission. So in that way I contribute to the measurement of the Earth, and in the end the mission is to understand the climate change of the Earth better, so that we can take the appropriate means and appropriate actions in order to ensure that the climate change doesn't go too far and that we can keep the world habitable. So the multispectral imager that we are developing for ESA is a 4-channel optical imaging system. So it's actually looking at 4 different colors on the Earth, and by combining those different colors, in the end, scientists can determine the air pollution, the air temperature, movement of air. And in order to do that, we built a system that you can see here, and actually the system can look at 2 ways. It can look at the Earth, so looking through this port down where the Earth is, and that it does for the four colors of the system. And then inside of this optical box, actually the colors are split into different detectors so that we can register what the Earth is doing. Actually, it's a fancy home-built camera, but one that you can launch and works in space. And there's one complicating factor, because we want to measure with extremely high accuracy. The detectors need to be cooled well below 0 Kelvin, so well below freezing point. And for that we have actually added this top plate over here, and that cools the entire system down to -40 degrees Celsius. And that's in the end quite a challenge, because we built the system in room temperature, and then it will be launched and it needs to be cooled down and still work as we have built it on Earth.